Good morning, my dear friends. I hope you all are doing great. So today, my dear friends, we'll be talking about the lattice enthalpy calculations. How to calculate lattice enthalpy. While doing experiment, my dear friends, when you are calculating the lattice enthalpy of dissociation, means you are breaking 1 mole of an ionic solid into constituent gaseous ions. Yes? And how much of energy is required for that? 788 kilojoules per mole. This much of energy is required. Correct? Then, if you make 1 mole of an ionic crystal from its constituent gaseous ions, that will be the lattice enthalpy of formation. Exactly opposite. Now the delta H lattice value will be minus 788 kilojoules per mole. So this will be the exothermic process. But it's not that much easy. When we perform such experiment in the laboratory, it's not that much easy. Like, you can break 1 mole of an ionic crystal and into the gaseous ions, then converting back gaseous ions into 1 mole of ionic crystal is a very complicated process. So the direct method cannot be applied to calculate the lattice enthalpy. Okay? So what we do actually, we are using now here a Born-Haber cycle. What is this Born-Haber cycle, my dear friends? Have a look here. Please focus right out here. It is an enthalpy diagram. Yes? And indirect method. As I told you that through direct method, yes, calculation of lattice enthalpy is very, difficult or rather impossible. Okay? So we are applying the indirect method to determine the lattice enthalpy of an ionic crystal, my dear friends. So what is this indirect method all about? It is this, the Born-Haber cycle. It is nothing but it's an energy diagram, my dear friends, or enthalpy diagram, because enthalpy is an energy only, energy change. So let us see how to do this. But before we do this particular kind of a thing, we can even apply the Hess's law here, my dear friends. So I will show you how to apply the Hess's law, right? So before applying the Hess's law, let us understand what we are doing. We can make any kind of ionic crystal, my dear friends, here. We can make NaCl, you can make calcium chloride, you can make magnesium chloride. So any kind of ionic crystal you can make here, and you can calculate the lattice enthalpy for such ionic substances. So I will take one example here to make you understand that what is this Born-Haber cycle and how to calculate the lattice enthalpy through the indirect method, my dear friends. Yes? Have a look. First of all, if you look here, my dear friends, try to focus it here. You will find out in this particular case, have a look here. We are taking sodium solid and half of chlorine molecule. That is a half mole of chlorine molecules in actual terms. So 1 mole of sodium solid and the half mole of chlorine molecules. We make them to react. And we are getting NaCl, my dear friends. I am making NaCl just in one step. So I can call it as one step formation of NaCl. It's a one step formation of NaCl, my dear friends. Look here, my dear friends, if you see, I have to calculate the lattice enthalpy of an ionic crystal. So this is my ionic crystal, my dear friends. This is my ionic crystal. You can take any ionic crystal, but I am taking here NaCl. And let us understand how to calculate this lattice enthalpy. First of all, in this step, you can see this down arrow. Sodium is reacting with chlorine to make NaCl, my dear friends. And how many moles of NaCl are formed? 1 mole. I told you in previous classes the formation of 1 mole of a substance from its constituent elements. The formation of 1 mole of a substance from its constituent elements is known as standard enthalpy of formation, my dear friends. So this is the standard enthalpy of formation. Okay. So I will apply here by applying Hess's law. We have. So this one-step formation is basically the formation of 1 mole of NaCl, I am repeating, from its constituent elements. So this is a standard enthalpy of formation, my dear friends. So I will apply here. We have delta H formation. And it's a one-step reaction, my dear friends. And what we are forming NaCl. So here NaCl is formed in 1 step. And you know that this is an exothermic process. Energy is released, my dear friends. The minus sign will tell you that this is exothermic process. Now, my dear friends, we will make the same NaCl. We will make the same NaCl, but in multiple steps. If you remember the Hess's law. We will make same NaCl, this NaCl solid, but we will make it in multiple steps. Now look here, we will go like first 1 step, 2, 3, 4, 5. After 5 steps, I am again getting, look at this line, I am again getting NaCl. So my dear friends, then I can calculate, you know what, the lattice enthalpy easily. Let us understand it. Cool? Have a look here. This was 1-step formation of NaCl. Then I will show you 1, 2, 3, 4 and 5-step formation of NaCl. NaCl formation in 5 steps. Then I will calculate the sum of the enthalpies. Except this one. Yes? This we can calculate then by reversing the terms here. Okay? Have a look. Let's take on the first one. Let us start the multiple step process. Yes? So, my dear friends, first of all, we have here sodium solid and we have half mole of chlorine gas. Let us leave this chlorine gas for time being. Don't touch the chlorine gas for time being, correct? Let us target this sodium. Sodium is present in solid state. So, how many moles of sodium I have? 1 mole. And I am converting sodium solid into sodium gas. So conversion of, here my dear friends, I am doing conversion of solid to gas. And solid to gas conversion, look here, solid to gas is known as standard enthalpy of sublimation. So you are doing here sublimation. And this sublimation process is basically 108.4. That means you require this much of energy to convert sodium solid into sodium gas. So obviously it's an endo process. This 1-step formation was exo, correct? Now you converted sodium solid into sodium gas, correct? Chlorine is already present in gaseous form, so no need of sublimation. Let us suppose if this substance is also solid, then you have to convert this also into gaseous state. But it's already in the gaseous state, so no need of converting it. So it will remain the same. Only sodium solid is converted into sodium gas. And the energy required here is known as standard enthalpy of sublimation. Yes? After that, let's have a look. Now, let us keep this chlorine same. Half of Cl2 gas and here also half of Cl2 gas. I am not touching the chlorine. I am keeping it same, my dear friends. But again, I am targeting the sodium. Look here, the sodium is in the gaseous state. Yes? And how many moles? 1 mole of sodium is in gaseous state. And I am converting it into 1 mole of sodium ions, my dear friends. So, what you are doing here, you are giving some enthalpy here. And what is this enthalpy? This is the standard enthalpy of ionization. Standard enthalpy of ionization. Can you focus it here? The standard enthalpy of ionization, my dear friends. You have here sodium. And you are making the sodium to lose electrons. Don't think that sodium is losing 1 electron, my dear friends. This sodium is basically 1 mole. This is 1 mole, my dear friends. It's like this, I will show you. Can you focus it here? Look here, you have 1 mole of Na, sodium. In which state? Gaseous state. Then you are applying some energy. How much of energy you are giving? You are giving 495.6 kilojoules of energy you are giving. This energy is your standard enthalpy of ionization. This much of energy you are supplying to 1 mole of sodium. 1 atom of sodium will lose 1 electron, correct? Then 10 sodium will lose 10 electrons. 1 mole of sodium will lose 1 mole of electrons, because energy is in terms of kilojoule per mole. You are not removing actually, 1 electron. You are removing 1 mole of electrons from 1 mole of sodium. Yes, so 1 mole sodium you have. You are applying this much of energy. So you will be getting 1 mole of Na plus. So you are getting from 1 mole of Na gas, you are getting 1 mole of Na plus. Yes? And how many electrons you have removed? You have removed, my dear friends, I can also write down plus 6.022 into 10 raised power 23 electrons. So these many electrons you have removed, my dear friends. Yes? If you write down this term here, it will become minus, like this. That means you are removing. If you take this molar term this side, it will become plus. So how many electrons you have removed from the sodium gas? 1 mole of electrons, my dear friends. And how much of energy is required? 495.6 kilojoules. So what is the standard enthalpy of ionization? The amount of energy required to remove 1 mole of electrons from 1 mole of gaseous atoms, my dear friends. Look here, this is 1 mole of sodium in gaseous state. So standard enthalpy of ionization means the amount of energy required to remove 1 mole of electrons from isolated gaseous atoms. So you removed 1 mole of electrons. Now you got 1 mole of sodium ions now, my dear friends, correct? So now you have a sodium ion with you. And I will place this sodium ion here. This is my sodium ion. Correct? Now what I am going to do, my dear friends, I have half of chlorine. Now I converted my sodium, which was in solid state, into gaseous state through sublimation. Then from gaseous state I removed the electrons through the standard enthalpy of ionization. I removed 1 mole of electrons. Now I got the sodium in the ionic state. So sodium in the ionic state, but in gaseous form, correct? I am done with the sodium. Sodium is done. But now I have to target the chlorine. How much of chlorine I have, my dear friends? I am half of the chlorine I have. If I take 1 mole of chlorine, let us suppose, then this is actually the bond dissociation enthalpy. This is nothing but this is your delta H dissociation. Correct? If I take 1 mole of chlorine, then the standard enthalpy of bond dissociation, or you can call it as bond enthalpy, or write it like this, standard enthalpy of dissociation, correct? So this will be actually, if it is 121, it will become double. Okay, how much is that? A double of this? It will become 242. It will become 242 if you have 1 mole of Cl2 here. But actually, what is my point here? If you are dissociating 1 mole of chlorine, Cl2 molecules, then this much of energy is released. But my dear friends, we don't have 1 mole of chlorine here. We have half mole of chlorine. How much? Half mole of chlorine. So the dissociation will become also half. So divide this by 2, it will become 1 to 1, my dear friends. So somebody may be thinking, sir, why are you using half dissociation enthalpy? The reason is simple. You have a half mole of chlorine. Yes? So if you have 2 moles of chlorine here, then it will become twice. Are you following my point or not? We have only half mole, that's why dissociation has become half. In some other examples, yes, this chlorine may not be half, it may be 1 mole. That time you have to write down bond dissociation enthalpy for 1 mole. Don't use the term half, because it's half mole here, so I am using half, standard enthalpy of dissociation or bond enthalpy simply. So how much energy is required to break half mole of chlorine. This is the energy required to break. Energy required to break half mole of Cl2. So this much energy is required, 121 kilojoules per mole. Now when you break half mole of Cl2, my dear friends, try to understand. I have not written it here, I have written it here. Try to understand. When you are breaking half mole of Cl2, you will get 1 mole of chlorine atoms. So you are getting 1 mole of Cl atoms, chlorine atoms. When you break half mole of Cl2, you are getting, my dear friends, 1 mole of chlorine atoms, my dear friends. Correct? Now, sodium is in ionic state, that we have already done. But chlorine has to now gain the electrons. How many moles of chlorine atoms you have? You have 1 mole of chlorine atoms. 1 chlorine will gain how many electrons? 1 electron. And 1 mole of chlorine atoms will gain how many electrons? 1 mole of electrons. Sodium has lost how many electrons? 1 mole. So we have here 1 mole of electrons. So this 1 mole of electrons will be gained by, lost by sodium, but will be gained by the chlorine, Cl2 gases. So my dear friends, look here at this particular point of view. So this much of energy will be released when your chlorine, Cl, this Cl gaseous 1 mole. How many electrons are released by sodium? 1 mole. So the chlorine will gain this 6.022 into 10 raised power 23 electrons. And it will give me Cl minus gaseous. So my dear friends, during this process, 1 mole of chlorine gas is accepting 1 mole of electrons lost by the sodium and changing into Cl minus. So how much of energy is released here? That is minus 348.6. So it's an exothermic process. This Eg stands for electron gain enthalpy. So Eg stands for here electron gain enthalpy. So now my dear friends, your chlorine, 1 mole of chlorine atoms, look here, 1 mole of chlorine atoms has accepted 1 mole of electrons, and change it into 1 mole of Cl minus. So this Cl minus is here now. Okay? And sodium was already in the ionic form. Correct? Now look here my dear friends, finally what we have. Finally now we have Na plus gaseous and Cl minus gaseous. Yes? So you are making these gaseous ions to combine now, Na plus and Cl minus in gaseous form. When you combine Na plus, remember Na plus gaseous plus Cl minus gaseous, if you combine, you will be getting NaCl solid. So you are getting here NaCl solid. Look at this arrow and look under this. You are getting NaCl solid. So Na plus gaseous and Cl minus gaseous are converted into 1 mole of NaCl. Yes? So this will be called as lattice enthalpy of formation. And we don't know the value of this. We have to calculate this thing only. This last step we have to calculate. Energy change in this last step. Because when Na plus gaseous and Cl minus gaseous combine, and when they combine, you are getting 1 mole of NaCl. So it's a formation of an ionic substance. So it will be a lattice enthalpy of formation. Yes? So we have to calculate here lattice enthalpy of formation. Once you calculate lattice enthalpy of formation, the dissociation is exactly opposite of this. So don't worry at all. So let us see how to do this all things, my dear friends. So finally, this one is a question mark. We have to calculate this thing through Born-Haber cycle. We don't know this energy value. So let me remove this thing here. Let me repeat this little bit, my dear friends. Let us see the one-step formation of NaCl. We combine Na and Cl to half mole, and we are getting NaCl solid just in one step. That is called as the standard enthalpy of formation of NaCl, just in one step. If we apply the Hess's law, my dear friends, it should be equal to sum of the enthalpy change in the multiple steps. So let us combine it. Let's take on the first one. We are converting sodium solid to sodium gas. Which energy is required here? Enthalpy of, standard enthalpy of sublimation. Plus, in second step, sodium gas is converted into sodium ion. 1 mole of sodium gas is converted into 1 mole of sodium ion. Which energy is required here? The enthalpy of ionization, this one. So delta Hi is required here. Plus, now in another step, my dear friends, after ionization, what happens? You are targeting now half mole of chlorine. Yes? And you are applying which energy? Bond enthalpy or bond dissociation energy you are applying. And you are breaking this half mole of chlorine into, come on, 1 mole of chlorine atoms, my dear friends. So obviously, which energy is required for this process? Bond enthalpy, but how much? Half. So you will use here bond enthalpy. That's a bond dissociation enthalpy, my dear friends. But we are calculating it only for half mole. So it is 1 by 2. If you calculate it for 2 moles, then 2 into delta H naught, correct? After that, what happens? Now, this Cl is 1 mole of chlorine atoms now. After bond dissociation enthalpy, from half mole of Cl2, I got 1 mole of chlorine atoms. Now, this chlorine has to accept the electrons. This chlorine has to accept 1 mole of electrons. And this 1 mole of electron is basically lost by the sodium. So chlorine has to accept them. When chlorine accepts these electrons, it will change into 1 mole of Cl minus. So it changes into 1 mole of Cl minus. And how much of energy is released when 1 mole of chlorine, remember, when 1 mole of chlorine in gaseous state accepts 1 mole of electrons and changes into Cl minus, the energy released is called as electron gain enthalpy. Yes? So chlorine, 1 mole of chlorine atoms are gaining 1 mole of electrons in gaseous state and changing into 1 mole of Cl minus, and at that time the energy released is called as electron gain enthalpy. So this much of energy is released. And what is the symbol here? So I will write down here plus delta H Eg naught. And finally, my dear friends, then you are making 1 mole of Na plus gaseous and Cl minus gaseous to combine together. Yes? And they make 1 mole of NaCl solid. So when 1 mole of ionic crystal is formed from constituent gaseous ions, 1 mole of ionic crystal is formed from the constituent gaseous ions, we call it as what? We call it as the standard lattice enthalpy of formation. But its value is not given, my dear friends. So we have to calculate this thing. So I will write down finally I have delta H lattice. And remember, this delta H lattice is nothing but it's a lattice formation. Yes? So my dear friends, according to Hess's law, you are making NaCl in one step, and here you are making again the NaCl in multiple steps. So same NaCl you are making, my dear friends. So the energy change here in one step for the formation of NaCl. The enthalpy change for the formation of NaCl in one step should be equal to the sum of the enthalpy change for the formation of same NaCl in multiple steps, my dear friends. That is our Hess's law. Are you following my point or not? Now, what is important thing here? That we are not aware about this particular term. We have to calculate this thing. All other values are given to me. You check it out here. The standard enthalpy of formation of NaCl in one step. How much is that? Minus 411.2. So this value is here. Minus 411.2 kilojoule per mole. That we know. So is equal to. Let us see the standard enthalpy of sublimation in multiple step process. So first step is the sublimation process. It's 108.4. So this first term is 108.4. Let us see the standard enthalpy of ionization. Standard enthalpy of ionization is 495.6. This is done and this is also done. 495.6. Let us talk about after this the bond dissociation enthalpy, that is 121 kilojoules per mole. So let us talk about this, but it's a half. Yes, my dear friends, so I'll take it as 121. But if we say that it's not like this half of 121, actually the total value is actually 121. Sorry for this. It's a half of delta H bond dissociation enthalpy we are breaking. You are breaking here half mole of Cl2. So already this value is equal to this. So don't write down half here. This entire value is actually, already we have taken the half of it. So it's equal to 121, my dear friends. Yes. So after that, delta H naught, that is electron gain enthalpy, that is minus 348.6. So it is minus 348.6. Plus, then you have delta H naught lattice, that we don't know. So we have to calculate this. So now, my dear friends, this value we have to calculate. If you sum up all these values, my dear friends, correct? And then transfer them up into this particular side. And finally you will get the value of this one. So finally, delta H lattice formation will be equal to, near about, it's a formation process, so it has to be minus only finally. So it will be minus 787.6. Okay, my dear friends. So exactly the actual value is 788. So you can take it round off as 788. So it's kilojoule per mole. So here, my dear friends, at this point I told you it's already half of bond dissociation enthalpy. Half of bond dissociation enthalpy is already calculated. It's 121. So no need of taking here half again. It's already half only. This 121 is this value only, half of bond enthalpy. So be careful here. So now, my dear friends, 787.6. So this is the standard lattice enthalpy of formation of whom? Formation of NaCl. Standard lattice enthalpy of formation of NaCl, because we are talking about NaCl here. And what will be the standard lattice enthalpy for the dissociation of NaCl? Exactly opposite of that, that is plus 788. Or you can write down plus 787.6. In round off it will be 788 only, my dear friends. So overall we calculated this particular thing by applying the Hess's law and by using the energy diagram given by the bond Haber. I hope everybody has understood this thing. Let me revise it for just few seconds. What I did first, I took the constituent elements and I made 1 mole of NaCl in one step. And the energy released was enthalpy of formation. This is your enthalpy of formation. And you are making NaCl in one step. Yes? Now you are making the same NaCl in 1, 2, 3, 4 and 5 steps. So you are making them in multiple steps. So 1, 2, 3, 4 and 5 steps. You are again making NaCl only. So what will be the sum of these enthalpies? That should be equal to the sum of the enthalpy change in one step for the formation of NaCl. So this term and these terms will be equal. Once you got the value of standard enthalpy of lattice finally, you can put this value here at this point. Take this value, put it here, and they will be equal, my dear friends. Please remember this. Take a note of this. Friends, now you have learned how to calculate the lattice enthalpy, the standard lattice enthalpy of formation of NaCl, my dear friends. And you got it as minus 787.6. It's an exothermic process, my dear friends. And you know you have taken the help of Hess's law as well for the calculation process. And now if you put this value here at this term, what will happen? The LHS should become equal to RHS. That is a common thing and all. Now, my dear friends, the Born-Haber cycle is basically the energy level diagram, or we can say enthalpy diagram. And it's an indirect method of calculation of standard lattice enthalpy of formation of an ionic crystal. When we know the formation of an ionic crystal, lattice enthalpy of formation, then we can easily calculate the standard lattice enthalpy of dissociation, because exactly the value will be reversed right out here. And it's not only for NaCl, you can use it for any ionic crystal, but you have to go through the same process. You have to apply the Hess's law, and finally you will calculate the standard enthalpy of lattice, that is the formation of NaCl. Okay, so my dear friends, with all this information you can go ahead and start calculating the standard lattice enthalpy of formation for other molecules as well. I think it has become, very easy for you. And be careful. Don't think that these are fixed values. The moles will change. Yes? In certain substances, they may use in place of chlorine, they may use oxygen. Like suppose in place of sodium oxide, you won't have chlorine, you will have oxygen here. Yes? So you have to calculate what? The dissociation enthalpy for oxygen. Or in some substances you may not have oxygen here. Yes or no? You may have bromine, or you may have iodine. Yes? So obviously the values will keep on changing, but the method is exactly the same. Please remember, my dear friends. Have a great time. Take care of yourself. Meet you in the next class. Yo.